Hello, hello YouTube. So this is day 4. It's a Saturday and it's day 4 of grinding low-level design. Uh, if this is the first video you're watching in the series, basically what I'm doing is I pick up a question of low-level design which I haven't seen before, and I implement the whole thing in each session. So this time also we're gonna do something similar. So let's go online and try to find a question. I think in the first session what we had done is we had created a framework in the first video. The idea was to use the framework to solve all the low-level design questions. What we had assumed is using a framework would streamline our thoughts whenever we get a new question, and it would save us some much needed time in each of those questions. So in the first episode we had done the framework, created a framework, and then used it to create a blackjack game. In the second one we created a Stack Overflow. We've created Stack Overflow with giving users the ability to post questions, answer questions, and add comments to questions and answers, and also rate questions. Then yesterday we did a library management system where users could where you could add books to the library and where you could add books to the library, you could add members, and members could borrow the books and return the books and something like that. Today, let's see what we're gonna do today. Let's go into problems. Let's find a problem to solve. We're gonna take a little bit of a lighter approach today since it's the weekend. I don't want to be too engrossed into trying to complete the exercise within 45 minutes to 1 hour today. So we are going to do a problem and we are going to start a timer, but we're not going to pay too much attention to the timer. We're going to take it in a little bit of a relaxed manner. So let's find us a question to get started. We have a hotel management system. I feel like a hotel management system, is it similar to a book borrowing system? Yeah, it's similar to the library management system we created, right? Because in that users can borrow a book, and then whenever a user comes to check if a book is present or not, we have to check if someone else had borrowed it, if it's there in the inventory. Similar to that, I think in a hotel management system, instead of books it will be hotel rooms. So I think this is something similar to what we had done. Let's kind of pick up something else, I guess. Let's see. What is this? LRU Cache. Okay, I think that means least recently used cache. LRU Cache should support the following operations, but insert a key value pair into the cache. The cache is at capacity, remove the least recently used item before inserting the new item. Okay, least recently used. And then you have a get function to get the value associated with the given key. If the key exists in the cache, move it to the front of the cache, most recently used, and return its value. Get the value associated with least recently used, most recently. Okay, when they say move it to the front of the cache, it's effectively they're saying that okay, just record that information that this was the most recently used key. If the key does not exist, return -1. Okay. Awesome. If the cache, so when we do put, we are essentially putting something into the cache, right? Yeah. Okay, so second requirement is that the cache should have a fixed capacity specified during initialization. And then we have the cache should be thread safe, allowing concurrent access from multiple threads. The cache, fourth is the cache should be efficient in terms of time complexity for both put and get operations, ideally a constant time. I think this is interesting. It's a little different from what we had done before as well. So let's kind of get into this one. I'm gonna do is I'm gonna create a new folder called LRU Cache, and I'm gonna create a file in it called question.txt. I'm gonna post the question here. Also, what I'm gonna do is I'm gonna pull up the framework and put it on the right side. And let's okay, so this is the question, right? Okay, if you are not aware what a cache is, you can kind of consider it as, for example, if you think about an application, you have a database where you're storing all your data, and if a user wants that data, you send a request to that database to get the data which you want to serve to the user. But as the number of users kind of keeps growing, at some point what ends up happening is the time it takes for the turnaround time it takes from the time the user has requested something all the way to when they get the data starts increasing, and that basically starts affecting the latency of the application. So imagine if, for example, if you go to YouTube, you see all the videos and thumbnails getting loaded, but as you scale up, and if you have not done anything in your architecture to handle that sort of scale, what's going to happen is those thumbnails and those images will take longer to come to you, and effectively this site will become much slower. So caching is just a way to improve the latency. What it does is it adds another layer of a much smaller layer in between. So each of your requests might not go to the database. So they add, like in caching, the concept is to add a smaller spaced but faster storage in the middle of your database and your user, so that when the user requests something, it first checks the cache, and if it's there in the cache, the request doesn't go to the database, and the user gets the response in a fast way. But if there's a cache miss, that there's nothing in the cache, if that particular data isn't there in the cache, then it's gonna go to the database and get it from there. So an LRU cache is basically a cache where whenever a new request comes in, it checks whether it's there in the cache, but if it's not there, it's going to add it to the cache and remove the least recently used entry in the cache. The reason why the cache isn't designed as a scalable thing is because it's expensive. For example, if you have you have a database which runs on maybe disk technology or some sort of a different kind of technology, but you add like a flash memory in between. Flash memory would be more expensive than the disk technology, so you don't want to store all your data over there. You just add it for a little bit of efficiency. If you still don't understand what a cache is, maybe there's an analogy I usually think of when thinking about a cache. At our houses, suppose we want to make something, to cook something, right? We require vegetables, we require masalas, we require all sorts of different things. One way to get these things is, for example, suppose you are making a red sauce pasta. So in order to make the gravy for that pasta, you'll have to get tomatoes. Now one way would be to go to the market every time you want tomatoes and get those many tomatoes from the market. But you can imagine that the latency of this operation is not favorable, because every time you want to make anything, you'll have to go to the market, which takes a little bit of time. So what we do is we keep a smaller storage at our house itself, and when we go, we buy produce for the entire week and store it in that storage which is closer to our kitchens. And in effect, that's basically what a cache is, that you have a form of storage which is closer to your point of contact, so that whenever you need it, you can just take it from there instead of going to the market. Yeah. So let's get started. I think in this kind of a question, one interesting thing is that they have mentioned the time complexity which is needed, which is given as O of 1. If you're not sure what time complexity means, it's basically a measure of how long an algorithm takes as a function of the input size. Input size as in the amount of data that the algorithm is working with. So for example, if for example for a sorting algorithm, if it takes 10 seconds to sort 100 entries, and if you double the entries, so you instead of 100 entries you now have 200 entries, and if it takes you 2 seconds to sort that, then the time your algorithm takes is increasing linearly with the size of the data. So you will get a O of n time complexity. If it doubles, or if it it exponentially goes up, like for example for 100 entries it used to take 1 second, for 200 entries it takes 2 seconds, I guess. No, for example, if it takes 2 seconds for 100 entries, and if you just, I think this is a incorrect example, maybe I should take 5 as an example. It takes 5 seconds for your algorithm to sort 100 entries, and if you move it up to 200 entries it starts taking 25 seconds. So it increases by a factor of n. Like it's not linearly dependent. Like when the input size increases linearly, the time it takes doesn't increase linearly. So in that case it would be an O of n squared time complexity algorithm. So here it's O of 1, so which basically means that the time it takes should not be dependent on the input size. So it doesn't matter how big the cache is, the time taken to do both these operations of put and get should pretty much be the same. Which basically means that we should not be going through the entries of the cache every single time, right? So we let's think about put operation, right? When we think about put operation inside a key value parent of cache, if the cache is at capacity, remove the least recently used item before inserting the new item. So in put we kind of have to identify the least recently used item, because if we don't identify that, I mean, like there are two situations, right? One situation is that the cache is mostly empty, right? It's not even filled up to capacity. In that scenario we can just add this entry in O of 1 time, because we don't really need to check anything, we'll just add this. But in the scenario the cache is at capacity, we will need to find the least recently used item to remove it. And basically this operation of identifying the least recently used item should be done in constant time if we want our put operation to also be done in constant time, right? Because every time we do a put, we'll have to identify the least recently used item, and then we basically have to remove that item and we have to add in our new item. Okay, then you have a get, which also we want to do it in a constant time. Get the value associated with the given key. If the key exists in the cache, move it to the front of the cache and return its value. If the key does not exist, return -1. Okay, so if it exists, we want to return the value, of course. Return find the key. We want to return the value, and we also want to update the some sort of a metadata which indicates when that key was used last, right? So last usage for that key. Okay, so I think when we talk about finding a value, like we have a key and we have to find a value for that particular key, it kind of makes sense to use a hash map over here. I feel find a key and return the value. Yeah, I think we should use a hash map, because inside a hash map, if we are using the key value pairs, it's probably gonna take O of 1. And update the last usage for the key. Let's think about this. Initially for the put, identify the least recently used item. One thing we can do over here is use a min heap. Right, in a min heap, the identifying the smallest item would take off n time, so I think that's why it makes sense to use min heap over here. Identify the least recently used item, and in this case, once we find the value, we basically, so assuming we're using min heap for our structure, when it says update the last usage for that key, effectively what we're trying to do is we are trying to possibly remove that element, remove one item from the hash map and add another item, right? We remove one item from the hash map and then we add another item. Effectively, for example, the in our heap, we are doing, like, we're creating the heap based on the last used value, which is, let's say, of type integer. Right, and when we actually find a key, what we're going to do is we're going to remove that particular key from the hash map. We want to so the problem is we don't want to remove the least used key. We want to sort of remove an arbitrary entry from the heap, right? And if we do that, we're gonna that the heap won't be a heap anymore, effectively. So what's gonna happen is, whenever we do that, we're gonna have to create a heap again to basically create that heap again. When we do a get, we will have to create that heap again, unfortunately. And what's gonna happen when we create that heap again? It is going to take an n log n time, because that's, I think it takes O of n time to create a heap. So here, if you take an element and it's not the topmost, like it's not the smallest element, so we are taking an arbitrary element from the heap and we want to update the count value, so we remove that element from the heap, and then add it again and then call heapify again. Yeah, this is a little dicey, because whenever we do this, it's not going to be an O of n time operation, right? Because we're not removing the interesting. If the cache is at capacity, remove the least recently used item before inserting, which is cool. But when you're doing a get and it exists somewhere in the middle, we have to update the value for that, and update the value for it to be the most recently used. So that value will basically come at the top of the heap, and I'm wondering whether we can just sift up that value. Online whiteboard. Okay, so suppose our capacity of our cache is something like, let's say, 4 elements, right? We got certain, I mean, suppose this is the input of like what is being requested, and suppose we request A, B, C, D. So if we request A, B, C, D, this is the least recently used is probably A, so we'll have something like this, right? Because the D was like it was used in the last turn, so it's only been 1, and this would probably have 2, this would probably have 3, and this would have 4, right? And the situation is that now suppose we get a B, and we already have a B over here. So if we can return the value for this, so we know we have that value, we can do that an O of 1 time, but then we have to create, like, modify this heap so that because this stops being a heap once we update this 3 to say 0 or something like that, right? And even these numbers are at 1, 2 and 4, so these will kind of need to get updated as well. Maybe we can use time, like maybe epoch time, because if we have epoch time, then we don't need to keep updating these values, right? Because this will just have the largest epoch time. So yeah, this can actually be a max heap, right? This can be a max heap, and the value which gets stored is the basically the epoch time, and the largest epoch time would be the least recently used item. That's the time when that cache was last used. So here, suppose this becomes like 0, it becomes a smaller value, and we return it. Can we just swap these two? Like, what happens if this guy would have come? We would have swapped these two and these two. I'm wondering whether there is a this will cause a problem in the future. That's all. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And suppose we got this 5, and this 5 became basically -1. Can we just sift it up? If we sift it with this, you will get 2 here, and we will get the -1 here, and then this will get shifted here, and then this would have 1, and this would have -1. But this is sort of incorrect, right? Or is it still heap? Right? How is it heap defined? 1 second. How is a heap defined? Each node is either greater than or equal to. Oh, then it's children, right? So here, even if this 5 becomes a -1, we kind of already know that this element over here is the smallest element. It has to be at the top, or the largest element if you're using epoch. So we know that in this example, this is definitely larger than this. So that's why we swapped it out. But can this violate the basic condition ever? Like, we didn't check it with this, right? And this will effectively become a child of that. But we know that that will always be smaller, so this won't break, this won't break. Yeah, we can just sift it up, right? If we sift it up, it should be fine. So if we effectively, we'll have to just sift it up, and sifting up that particular entry would probably take O of n time, right? Because in the worst case, it won't take O of n time. It would probably take log of n time, right? Because there's no way it has to go through every single element, unless your list is like this, and we pretty much updated this last one. It will just exchange. Yeah, I think worst case it can actually take O of n time, right? In which case, update the last uses for that key. It's not gonna work. That's interesting. How do we do this? Identify the least recently. It seems like it should be using a heap, because we are trying to identify that. But whenever there's a hit, we kind of need to handle it in some manner, right? It's going to take log n time effectively, not constant time. Actually, O of n time at the worst case. I mean, not all of the cases, but you can. Is there some other data structure we can use, maybe? Alternatively, the only problem with this is, I guess, one second. So here we wanted to remove the least recently used item, right? Least recently. That's the item which we would remove, but in order to update the hash map, it's gonna take some time, unfortunately. If you think about it, the operation will actually take constant time, because when we find a key and we get a hash map, we get a value, it just returns. This updating the hash map itself can happen even after we return the value, right? We can have separate threads to do that, or we don't really need to wait for the hash map to wait for the heap to become complete again before returning the value. Like, for example, we can keep it in a message queue as an action, and then yeah, I'm not sure. Let's see. No, it'll have to be over here only, right? Because concurrently or in parallel, if another request comes in, we kind of need our heap to be in the correct state. Yeah, that's interesting. Suppose we have it sorted instead of having it like a heap. Suppose we have it in a sorted array, right? Identify the least recently used item in the sorted array. It's easy. It will be the first item. You can remove that item and add in our new item. The new item which we are adding is the most recently used item, I guess. So we know that in the array it's going to be added to the last position. So these operations do work out in a sorted array. The other one is get, where we find a key. Okay, in the array, will we be able to find the key fast enough? So it's a sorted array, but oh yeah, so basically finding a key would take O of n time, right? Suppose we do a hash map, we do a dictionary, we kind of need to do a dictionary over here. So we use the dictionary to return, and then what we have to do, we have to update the last usage for that key, which means that value we have to put it at the end of the array because it was recently used. I'm not able to visualize it. It's kind of, can I erase this? Or maybe it has to be a faster. Oh man, that's just. Anyways, let's just think about this for a second. So what I was getting at is, suppose we are using it in an array, right? We have a hash map also. We have a sorted array, and we also have a hash map. Putting an element in the cache is simple enough. We know whether we want to put it. We can remove this element and just add it over here. But suppose we are fetching an element, so in the hash map the fetching takes off one time. But now this array needs to get updated because that element, if there's a key 1 to value 1, that element, wherever that element is present within this array, that needs to be shifted ahead, right? This entire thing has to come back, and this thing needs to be shifted ahead. And that's probably going to take an O of n time. Interesting. So can we how will we find this element? So maybe the index of this element is also stored here. It stores the value as well as the index. If that is true, with the key we should be able to find that element at least. And then in order to how much time would it take for to shift this element towards the end and this entire thing over here? Basically what we are doing is we will keep shifting these elements here and then add this towards the end. So I think it would still take O of n time worst case, right? You know, one thing I was thinking about is, like, instead of actually shifting this, we can just invalidate this one and add an entry over here. And but the problem with that was that the cache capacity gets a little messed up, because now we are basically adding 1 to the cache capacity, but we want to use the same capacity. Didn't make sense to use a heap. The problem with the heap was just that when we update one of the elements in the middle of the heap, it was taking log of n, or worst case O of n time, to make that back into a heap. Let's look up what the solutions are. Are they okay with doing it low level design? Let's kind of look it up, because I feel like I'm missing something very small over here, right? Or is it something we didn't even think of? Let's see, our LRU design considerations. LRU cache needs to be initialized to specific capacity. Methods updates, LRU behavior. Oh yeah, we were on. Okay, so it's not that we thought about it incorrectly, I think. Okay, so what they're saying is that, yeah, so we definitely need a hash table to return it, but the problem is that when we update, what is this? This is a doubly linked list, least recent. Oh, we were close. Okay. So this array method is kind of fine. We said that in the array, the problem is it would take O of n time to get this node to the end. But instead of an array, if this is itself a doubly linked list, then we can do it in like constant time. Oh, got it. We were on the right track, right? We have a hash map. So the hash map would actually store a reference to the node itself, right? So we were able to identify this. The problem was that moving this to the end was in an array, it would take an O of n operation, worst case. But when you think about it on a doubly linked list, we can just directly put it in the end. Yeah, that's interesting. Come to think of it, do we really need a doubly linked list? Why can't we do it using a singly linked list? When are we using the property of that doubly linked list? The other operation was adding, right? We can just, when we are adding, yeah, why do we need a doubly linked list again? Is there some case I'm missing over here? Because it sort of feels like this should be possible with a singly linked list. Oh, it's frozen, but okay. So suppose we have, why is this not working? Yeah, so suppose we have these nodes and we have a hash map. Hash map stores key to value, and it also stores the reference to the node, right? And for example, what were the operations we were performing? We were performing one, insert a key value pair into the cache. If it's at capacity, remove the least recently used item before inserting a new item. So this is ordered, so this is least recently used and this is most recently used. So suppose we create another node and we say that, okay, we basically want to replace, no, 1 second, we don't want to replace, we want to remove this and we want to add this to the end, right? And that would be an O of 1 operation, even in a singly linked list. In order to remove this, we have a reference to head, which we are just going to update to this, and we'll keep a reference to maybe tail, right, the last one, and we'll just update the tail.next to our newly created node. So this operation works. The other operation is when you're trying to find a particular node, right? And if it's a cache hit, suppose there's a cache hit on this, and from this key value and reference, we are able to get a reference to that particular node. Now what do we want to do? We just want to move this node to the end, right? So here, in order to move this node to the end, this has to point here. That's about it, right? Yeah, if we can make this point here and this, we can just add to tail.next and update the pointer to maybe none over here. Yeah, I don't think we need a doubly linked list for this. Singly linked list should be apt, right? Am I missing something? Why do they say that you need a doubly linked list for this? Store elements in a specific order with least recently used at the bottom. Doubly linked allow us to move any element to the top in constant time, unlike a normal list, array, or slice. This I understand, that we can't do that with a list or an array, but we can do that with a singly linked list, right? The doubly linked list allows us to move any top in constant time. And that's true for a singly linked list as well. Accessing an element would still take overtime. That's why I used a hash map to store, which is correct. I feel like we can still just use a singly linked list for this, right? How will we initially maintain? Okay, what about the first 5 entries which are added? Yeah, we can just like keep adding it to the end, right? I honestly feel like we can just do it using a singly linked list. There's no specific reason as such why a doubly linked list would get used over here. LRU cache using singly linked lists. Most LRU cache tutorials emphasize using a doubly linked list and a dictionary in combination. The dictionary holds both the value and reference to the corresponding node on the linked list. When performing a remove operation, we look up the node from the linked list dictionary and we have to remove it. Now here where it gets weird, most tutorials argue that we need the preceding node in order to remove the current node from the linked list. Oh, that's why. Okay, got it. So, here the problem is we have a reference to this, which has a reference to this, but this we cannot update if we don't have. Okay, got it. Yeah, I think we do need a doubly linked list. But his question is, here's where it gets weird. In order to get the current linked list, this is done in order to get O of 1 time. However, there is a way to remove a node from a singly linked list in O of 1 time. Set the current node's value to the next node and then kill the next node. But how can you remove an element from a singly linked list in constant time? To delete a node from a single, we typically redirect the previous node's next pointer to the subsequent node. For example, we remove the node 3. We would adjust node 2's next pointer to node 4 directly. This effectively excludes node. However, a challenge arises when we cannot access the previous node. As in the case in the specific problem, since we only traverse forward from the node to be deleted, the conventional deletion measure is not feasible. Scenario I can't access this problem goes data overwriting. To circumvent this limitation, we can apply alternative strategy by comparing the original linked list with the desired. Notice that the nodes following the target node will be shifted from. Okay, but you have to shift it then, right? Copying the data from each subsequent node into the predecessor, yeah, this would take over n time. This is it's very similar to how you would do it in an array. So yeah, I think we do need a doubly linked list. Okay, I think we understood what is to be done. We can probably get started. Let's create a file called main.py, and you know what all do we need? We do need a doubly linked list. Is there a Python library for a linked list which I can just leverage? Doubly linked list in Python. Or do we want to write our own thing? Let's pick it up from here. We'll modify it as we see fit. Okay, so we have a node, and the node has data, previous, and next. We can rename the data. Should we rename the data? What would the data even contain? Would it contain? So it should contain some sort of a value indicating. Actually, it doesn't even matter, right? If the what if we just keep the value? Yeah, we can just keep it as the data. Because the ordering we are anyway storing in a linked list, so I don't think we actually need to sort it out. We can just, yeah, we'll keep the size of the linked list here for sure, right? So we do need a size which is equal to whatever size we're going to pass in, which will be of type integer. And then we have an append function. What the append function do? It takes up a new node if not self dot head, if the head does not exist. Self dot head is equal to new node, tail is equal to new node, which makes sense. When we create a new node, the previous and next references are none. Okay, otherwise when we are appending, it takes self dot tail dot next to the new node, and new node previous to the tail. So this is basically appending to the end of the list, right? This is appending to the end of the list. And so basically whenever this is called, we kind of also need to update our size. Dot size plus equal to 1. And there is definitely a situation where we are appending, where we reached our max. Okay, so we need a size which is initialized to 0, and this is actually max size, right? And this defines how big the doubly linked list can actually be. Dot max size, right? And max size is equal to whatever was passed. So now suppose in this situation we know that self dot size, so if self dot size is smaller than self dot max size, in that case I feel this we can do, right? Because I mean, if the size hasn't even reached capacity, then we can always add another element to the end. But you know, if it has reached capacity, in that scenario what we want to do is we want to effectively we want to remove the first element, and we want to add new element to in the end, right? In the end. Awesome. So in any case, we need a new node, because we're not going to say that, you know, just because the capacity is breached, we're not going to add a new node itself. So we definitely need a new node. And do we want to check if this node exists? What were the operations we were supporting? We were putting a insert a key value parent to the cache, and then you had get, and does get also just insert a key value pair? No, okay, it returns -1 if it's not there in the cache. Awesome. So we get main, and I think, okay, we're doing fine. So removing the first element. So in our doubly linked list, the first element basically is our head, and we would want to remove the first element. I guess there is a condition where it's possible for max size to be a single element, in which case once we remove the first element, basically our list becomes empty, right? But when we remove the first element, what happens? Let's kind of look at our whiteboard once again. Okay, so we have our linked list, and we want to, this is head, this is tail, these are doubly connected. So if you want to remove this element, basically what we're doing is we want to do head to be equal to element dot next, right? And we want to do element dot next dot previous to be equal to none, right? So basically the pointer coming back from here should be set to none, and h needs to be set here, and basically element dot next should be none after that. So the three statements basically, right? We want our self dot head to be element, the element itself we're referencing through head, I guess. So we get self, 1 second, we'll lose access to the element, right? So let's just say head is equal to self dot head, right? And then we do self, we do a head dot next dot previous prev, okay, previous is equal to none. So we changed heads next and back to that, and then now we say that self dot head is equal to, actually we can just do it here itself, I guess, right? Head is equal to self dot head dot next. Will this do it? No, I think that it'll result in some sort of a memory leak. Node to remove, right? And node to remove initially would just be self dot head, right? And this node to remove dot next would be none. Node to remove dot previous would also be none. I guess this node to remove would still sort of exist, although we won't have access to it. Maybe you can, there's a way to free up space in Python in a linked list. If I want to remove an element, remove a node probably, how do I free up the space it uses? Yeah, it's probably automatic garbage collection. Oh, okay, there's a delete node, automatically deallocate the node. So we can delete the node, right? Delete node to remove, I guess. Okay, so we took the node to remove, reference to that, and we said head, or we can even do just node to remove next previous is none, and then we say that head is equal to head dot next. To improve a little bit of readability, we'll just say it's node to remove dot next, and then we basically remove the node. Okay, awesome. And we want to add a new element in the end, right? And the new element we already have. Adding a new element should be similar to this, to be honest, right? Isn't this just adding a new element? Without updating the size, of course. So, this was the condition where we haven't reached capacity, and this is the condition where we have reached capacity. Assuming that the capacity is more than 1, I think this first scenario is not going to happen. So we can probably just make do with these 3 lines. So tails next is equal to the new node dot previous is equal to tail, and self dot tail is equal to the new node. Awesome. So we have the append functionality. We can now effectively add stuff to our linked list, right? So the most frequently, the last used item is actually going to be on the tail of our linked list. It's going to be on the right end of our linked list, and the oldest, the least used item is probably going to be the first element on our linked list. So we got an append function where we are adding to the end, and this is a prepend function where we add to the beginning. We don't need this. We never actually add anything to the beginning, and we have an insert after a particular node, which again I don't think is necessarily needed. so we can make do without this. Insert before, we don't need. Delete node, I guess we don't need now. We do need some function, right? We need a move to right, move to tail function, I guess, which takes in a node, and basically this node we want to shift to the tail, right? So how do we do this? So in order to shift this node to the tail, assuming we have the node from our hash map, or we have to store it in a hash map itself as well, probably. Okay, we will store it. I think during append we kind of also have to store a reference to this in the hash map. We'll see how to do that. We'll create an LRU class probably which will use this doubly linked list, but move to tail function is still needed. So in order to get a move to tail function, we need the reference to the node which we have, and we do node dot previous dot next is equal to node dot next. So the previous the node behind our node, we modify the next reference to go to node dot next, and then we do node dot next dot previous is equal to node dot previous. So now we kind of remove this node in a way, and now node dot next is probably equal to none, and node dot previous is probably equal to the current tail, right? And then self dot tail will probably be equal to node. That's pretty much it, right? So if you pass in a node, it should be able to move it to the tail now. And then we have a print list function which takes current and just prints out all the data. Awesome. So we have a doubly linked list with our needed functionality. We have a node class which is probably being referenced over here. Ideally it should have been referenced here. I should add like it's of type node. Yeah, I think we'll revisit if we feel there's a problem over here, but I think for now it's fine. Okay, so we also need a hash map. We'll just maintain it within whatever class we're using for our LRU cache. So let's implement LRU class def init. Awesome. Self. Will the LRU class get initialized with anything? No, right? Yeah, I think we're okay not initializing the LRU class. I guess. Are we taking the max size? Yeah, we do take the max size, right? So let's initialize it with max size then. And it probably creates the doubly, what's the spelling of doubly? Doubly linked lists. Doubly linked lists. Doubly. Oh, it was correct. Okay, doubly linked. Let's just call it doubly LL, right? Or DLL. Double linked list, right? And we probably want to initialize it to our doubly linked list. Does it take? Yeah, it takes max size, right? So let's pass in our max size. Also, we want to maintain our hash map, right? Which just started as an empty hash map. So currently there are no elements, so we keep it as an empty hash map. Then we have, what functions do we need to support in the LRU? Add element, self data, which is, let's say we are working with integer data. Right, key value pairs we're dealing with, right? When we do have a key. Let's say our key is an integer, let's say our value is a string. We can keep it as anything. For now, let's just keep it like this. So we do have a key value pair. What all do we need to do in add element? Add element, let's just rename it add entry LRU dot add key value pair. Let's make it explicit, right? Oh, 1 second, they've already given us what to use, right? Yeah, it's a put method. Anyways, we have to use a put method over here, and we would also have a get method over here, which would probably take in a key, right? And let's define the put method. What all do we need to do over here? We need to create a node and append to the DLL. We need to add reference in the hash map as well, right? Correct. So let's create a node then, right? Node, what does it need? It needs some sort of data, right? Which would be our value, I guess. How does the node store data? It's data, yeah, so the data, let's keep it as a string data. Okay, so now we have our node. Then what we do is we create a node, append it to the DLL. So .dll.append, pass in the node over here, and also we update the hash map, and we say that at this particular key we need to add the node itself. Awesome. And we did all of this. So this basically, this line is over here. So we have the put method in place. Now let's kind of code out the get method. The get method was, 1 second, why is this giving an error? Oh, it's because, okay, get method was that you find a value associated with that given key. If the key exists in the cache, move to the front. Okay, fine. If it doesn't exist, return nothing. So first let's check if the key exists, right? So if key not in self dot hash map, we know we don't have the data, so we just return -1, right? If you're here, then the key definitely exists. We get the node instance, I guess, from self dot hash map by passing in the key, and we have the basically node instance, which should give us the value to return as well. Node dot data, that's the value to return. And what we need to do is we need to sort of update this node in our DLL as well. We define a method for this, move to tail, which takes in our node, right? So that's it. And this node.data has to be returned, so we'll just return it directly instead of creating a new variable. And suddenly this function is also sort of done. Is there anything else which is needed? I think this will just work. Let's write some sort of a driver code for, to make this work. We'll call our cache, we'll initialize our LRU class, which takes in a max size, let's say, max size of 3. So 3 elements we can store in the cache. So now I guess we add elements. Let's also print this out. Let's see what happens, right? For LRU, I guess we haven't added a toString function. Def string self, that's pretty much it. And we need to print, does our doubly linked list have a toString function? Oh, it has a print list function, which is good enough, I guess. And it does, okay, so let's just use this then. So we do a self.dll.print lists. Let's just print out the list for now, right? Or do we want to print out the hash table itself? So we can do it real quick. For key and value in self.hashmap.items, I guess. We print out the key, but the key is like it's an integer, and we add some sort of delimiter, and then we add our value, not wrapping the value in a string function, because it is, I think it'll always be a string. Awesome. So we created a cache, and then let's print it, right? So if we do print cache, and let's run this code, let's see what happens. Okay, so we have to go into our LRU cache, right? And Python main, we ran it. Some sort of a problem. Oh yeah, okay. Basically these type of functions need to return a string. Although we're not printing the string which is returned. Okay, so nothing gets printed, which I think is correct, since our cache is empty and this is not really print list does not print none values. So I think it's correct. Plus the linked list is basically empty at this point when we initialize it. Awesome. So let's add a couple of elements, right? Let's add some entries. Okay, so we have cache dot put, and let's put in 3 entries. So we put in 1, and let's just copy and paste these things. This becomes 2, this becomes 3, right? This is 2, this is 3, which is, I think it's great. So we have this, it should work out. And at this, actually we should even add one of these here just to see printed out after adding 2 elements, right? So awesome. So I think it works. So we had wait a second, what did it print out? It printed out 2 elements, which are those node objects. Then it printed out the hash map, which is 1 pointing to the first node object, and 2 pointing to the second node object. You can look at the this value, this address, to see that it's the same. And then we added 3, and then this also has 3, which is great. And now let's kind of do a cache dot get, right, which takes in a key. So let's do 2 from this. Actually, in order to make it a little bit more readable, let's do this when we are printing out the list instead of just current dot. We're printing current dot data, right? So print list would come over here. Are we not populating the data? Because we are sort of printing out the data, right? So when we put an element, we append the node, and we have the value to the node, right? So value node dot data should actually have it. I'm not sure why this did not get printed. The data somehow still contains, it just says it's a node object. Maybe because the node object does not have this type of function. Like if I return self.data from here, will that actually make a difference? Basically it was calling the string function, the string version of the node object, which by default just shows the object, the actual object implementation. So here we can see that we have 1, 2. Let's also add a new line between the two. So let's not over here, but rather over here. Let's, I think, add a new line character. Let's add actually 2 new line characters over here, and effectively it should. Okay, so I think 2 new lines is a little bit too much. Let's do 1 new line. So in our use case, we do cache.get, right? Let's print got value for key. Value, right? Got value. Okay, we got value, and then here we do a cache of 2, and then we print out the cache again. Awesome. So now if I run our program, let's see what we have over here, right? So we put in two elements and we printed it out. So we had 1 2 and 1 2. This is the hash map, this is the linked list. Then we added another element, so got 1 2 3 and 1 2 3 and 1 2 3. And then there's some sort of a problem saying that node.previous.next none type object has no attribute next. This happened on line 42. So there is a situation where node.previous is actually equal to none. Can node.previous be none? Yeah, if it's the first element, then yeah, I guess there's a possibility that, you know, the element we found, for the element we found. So the move to tail function is actually not correct, right? What happens is we got node.previous can actually be none, in which case it is the first node basically. If it's the first node, then basically instead of doing node.previous.next, we have to do head is equal to node.next, right? So we can check over here that if head is actually equal to node, right? If self.head is equal to node, in which case we, you know, instead of doing this, we would have a situation where self.head is actually node.next, right? Otherwise node.previous.next is equal to node.next, and then we have node.next.previous is equal to node.previous, which, you know, if in the scenario where the first element would be null, which is fine, right? Node.next.previous is equal to null for the first element, and then you get node.next is equal to null, and you get node.previous is equal to tail. So okay, you took out the node and then you put previous as tail, and tail self.tail is equal to node. I think. Okay, so line 45. No, but we already sort of checked, right? If head is equal to node. So it's saying that, you know, it's not the, you know, when did this happen again? What did we even do? We tried to get the value of 2, which is sort of in the middle, in which case what should have happened is that it should have kind of gone here and said, you know, that node dot previous dot, which is 1 dot next, should be node dot next. This actually node dot previous should not be a none type, right? So probably there's a problem while we are adding the nodes. When we create a new node, if self.size is strictly smaller than max size, so there is more space, we do self. If not of self.head. So what does that even mean? So if self.head is equal to none, right? Then basically we are adding the first node, in which scenario what's going to happen is we're going to do self.head is equal to the new node and tail is equal to the new node, and if it's not the only node, then it's going to be self.tail dot next is equal to the new node, and new node dot previous is equal to self.tail, and self.tail is equal to the new node, which also sort of makes sense. And then you have a situation where this capacity has been reached, right? But this, you know, honestly, this code probably didn't execute, so I'm not sure why this is causing a problem. Yeah, at line 45 it seems to be causing a problem, right? Line 45. Oh, it's okay. In move to tail function, it's causing a problem. It's saying that the node.previous doesn't really exist. Node.previous should be equal to the node, right? When we are adding elements, do we set the previous properly? Yeah, previous is equal to self.tail, whatever the tail points to. Huh. I think I'm just missing something small over here. You think Gemini can give us the answer to what we are missing? There is a small bug in the codes below which implements an LRU cache, right? Can you tell me what the bug is and how to fix it? Oh man, the code didn't get pasted. 1 second. Okay. The bug in the code lies in the put method of the LRU class. Here's the problem: when you add a new node to the doubly linked list using .append node, it checks if the size is less than the maximum size. If it is, it simply appends the new node. However, if the size is already at maximum, it removes the head node from the list and then appends the new node to the tail. So what's the problem in that? The issue arises because the get method relies on move to tail function to update the recently accessed node position in the DL. But the put method, when removing the head for a new entry, doesn't update the reference in the hash map dictionary. What? Why would I need to append it in the hash map? Wait, what's going on? So append we use over here, right? When we do a put. So when we call append, we call it with the node, and the node where we are keeping it in the hash map, right? Is there a scenario where this doesn't work? Yeah, we do use move to tail function, but in the move to tail function, we're not really creating a new node, right? We're just bring that node to the tail. Yeah, that's so weird. I don't think that should have caused an issue. Interesting. Let's we'll need to print it out in order to check what's going on. Wait, what? one string type node. When did it return? I'm returning the string itself, right? Why did this cause an error? Print current.data, and then we printed the previous and the next. And is it, I don't know, what does end do? Python and parameter and print. Give me an example with multiple elements in it. Yeah, I think the end is also fine. I mean, why is this giving an error in the first place? It starts printing it, right? Oh, it starts printing it. It prints out 1 and the previous, which is none. And it says current.next, and it says that wait a second. Interesting. And current.next says it gives cells.data, right? I don't see why this would cause an error. It's saying data is of type node, is it? Node and string. Self.data should be string, right? Yeah, data is of type string. Why is this considering this as a node type? That's so weird. Current dot. So where do we are probably populating the node somewhere, right? We pass in the data when we create the node object, and it just sets it. Data is equal to data. So when we create a node object, during append, we were passing in the data, which should be of type string, right? Okay, we use append over here. Oh, we're passing in the actual node object over here, which is one second. We create a node because we want a reference to it, and then we call dl.append with the node value. That's what's causing the problem. If we just give the value, then I think I got the issue, right? Because effectively the problem is we're creating a node inside this, and we shouldn't do that. We should just get a node instance from here, right? When we do append, we should get the node which we want to do and just use that node, right? Because when we do an append at this, where's the append? Yeah, now we create a node and then we append the node. All right, we don't have to create it inside that function. Oh, that was problematic. Okay, so let's see what happens now. So we got 1. What did I do? Yeah, I printed out the previous and next, right? Which makes sense, right? For the first one, the previous is none and the next is 2, and for 2 the previous is 1 and the next is none, which makes sense. And then we added another, so we get 1 2 3 with none and 2, 1 and 3 and 2 and none. And then this is the hash map, and then got value 2. So I think it worked out, right? Like, did it just work out? Looks like it worked out, because we got value 2 and then we printed the cache, right? And the consequence of getting the value true should be there, because now since we got the value 2, effectively we accessed this node, right? And once we have accessed this node should have been shifted to the end. Unfortunately, it's not there. So there is some issue, right? There is an issue with the append to end function. Like for example, when we actually get the value, the move to tail function. Okay, so we get the node and we say the w linked list move to tail this node, and it doesn't do it basically. So there's some problem in this code. In our in our situation, it was like the middle node. So self dot head is equal to node would be false for 2 because it's not the head node. So if this is false, then it would go here and say that node dot previous dot next, which is 1 dot next, should point to node dot next, which is 3, which actually happened because 1 has none and 3, so till here it's fine. Then we got node dot next dot previous, which means the previous of 3 should be node dot previous, which is 1, right? So this also worked out fine. Then we had node dot next is equal to none. Okay, which is, I guess it's okay because we are appending it to the end of the list. Then we had node dot previous. Node dot previous is equal to self dot tail. Yeah, I think this is incorrect, right? So node dot previous should also be ideally none. Oh, okay. Node dot previous is equal to self dot tail, and tail points to 3. So node dot previous got updated to the tail, and then the tail is node. But I think we missed one step where we had to do self dot tail dot next should also be equal to the node, right? I think this is one step which kind of got missed out. So now it should work, right? Now we get, now it works. So now in our cache, because we accessed 2, the 2 came over here, right? And now suppose we put in 4. Okay, so we put in a 4 and then we print out the cache. Let's see what happens. It should ideally, like we're at this point and we're putting in a 4, it should remove the 1 and put in the 4 in the end, right? So we should have 3, 2, 4 in the end. 3, 2, 4. Nice. So our LRU cache basically works. Yeah, I think it works. I think one thing we didn't do is that the question also kind of asked for concurrent access with multiple threads, and how you would go about that is similar to how we did it in other questions. Like for example, in the library management system, we import threading and we use threading.lock to get a lock inside the class, and then whenever we are accessing any of the data, for which in our case would be the W linked list or the hash map, we add this inside with self.lock. So what that does is it should kind of keep it memory safe. So for example, over here in the LRU, we can do import.threading, we can do self.lock is equal to threading.lock, right? And we just, whenever we actually access the DLL, maybe not while printing it, but at least while putting stuff, we get with self.lock, and then we can do it like this. Right? And ideally, like for example, when we're creating a new node that's not technically in our critical section, so we can keep it outside as well. Whenever we are accessing the data, that needs to be, that's considered to be in the critical section of our code, and thus it's where we have to acquire a lock before we modify. Like even here, this part can actually come over here, and then if the key exists, we are accessing the hash map, and that's why this works. Even in the string function, we should probably we can use something like this, right? And it should not have made any difference to our code. Oh, one thing is interesting. So when, yeah, I think one thing we missed out, and it's good that we printed it out in the end. Over here, when we add 4, it does add it to the end and it removes the 1, but it actually doesn't remove it from our hash map, right? So most of it is working, but you know, since we check our hash map initially when we try to get an element, when we do this put 4, it creates a node and it does dll.append. One second. Okay, and this append would essentially just handle removing the first node if you know that situation arises. So here we would also have to do 2 steps, right? We have to delete the key from the hash map, I guess, because now it won't exist, because append would actually just remove the tail. But the thing is, in order to remove it from the hash map, we kind of also need to know what was the key, right? Because we're not actually maintaining it. So append should ideally, maybe append should just return that key value, right? So maybe it should return the value. So you know, append works, and then by the, you know, this is the situation where it's not removing anything. And so in this situation it should just return none, and this is the situation where it does return something, in which case it should return the you know, this node to remove dot data, right? So you know, data to remove is equal to node to remove dot data, right? And this data to remove should probably send over here, and yeah, so over here this append function would get some data, right? And only in the situation where we removed, so if data is not equal to none, then we basically have the value that needs to be removed from the hash map. So Python remove entry from dictionary using value. How do we do that? We have let's go through the entire dictionary and remove it. Is it? Keys to remove. Oh, it removes all of those keys. No, so we just, like, we are assuming that key value pairs are unique. So yeah, I think we just need to do this. Oh no, it's finding the keys as well, right? So it goes to the dictionary to try to find where that value matches and then deletes it. I'm wondering whether there's a faster way, better way, because you know, in this method we'll have to go through the entire hash map to kind of find it. Maybe it's better to just our doubly linked list is not aware of the keys, unfortunately. If we would have stored the key as well in the doubly linked list, maybe it should have worked, but since we are not storing the key, yeah, I think ideally we should have just stored you know, key value pairs in the node, and then we could have just returned the key to be deleted, and it would have been much simpler. But in this, the problem is that since we don't have access to the key, we just have access to the value, we are actually are gonna have to go through it. Like for example, we'll have to write for key value in self dot hash map dot items. Yeah, this is like a suboptimal way to do it. Ideally, you would want to store the key and value both in the linked list and then return it over here and then use that key to delete it from the hash map. But since we don't have that, we'll do this. And if value equals the data, then we know that this key needs to be deleted. So we'll have a key to delete is equal to none, and we'll say that and this will exist, right? Because we know that this exists. This condition will be met with this key. Break out of the for loop, right? And let's keep it inside. Yeah, and we do self dot hash map dot Python remove from dictionary using key. Let's just delete that entry, right? Let's just delete self dot hash map at the key to delete. Is that it? Yeah, so that's how it's gonna work now. Oh, there's some problem. Okay, key to delete input key error none. Huh. So this is none. It didn't get set to key for whatever reason. So value was never equal to data. Hashmap dot items, this key value. So this data append did return that, right? Yeah, it returned the data to remove, right? Not to remove the data, to remove. There is a situation where it returns none, but if append returns none, we do check for it. If data is not equal to none only, then we kind of get into this. So we know that the data exists, and inside the hash map, the value should probably also exist. Key to delete. So yeah, this didn't get hit for whatever reason. That's so weird. Why would it not get hit? One second. Let's just. So towards the end of it, we have 1, 3, 2 in our linked list, and we have 1, 2, 3 in the hash map. And we did a put on 4. Line 92, that's a problem. So when we did a put, it created a new node. It probably appended the node. DLL.append did return some data, I guess. Just print out the data. Yeah, so it came out to be 1, which is correct, which was the tail. So we definitely had data, and then it's checked. If data is not equal to none, which is true because the data was 1, it went here, set key to delete is none, and that went through the hash map items, and the data was never equal to the value was never equal to data. How is that possible? Checking value and data. Looks like I'm missing something here. Yeah, so the data was 1 and it started checking, and it should have just, the first time it checked for 1 and 1, and it should have just have broken out of it, right? What's happening over here? Is it not? Why is it not? Oh, this time it removed it. Checking. Oh yeah, this time it worked. So one of the data wasn't a string, it seems. Huh. Interesting. Let's see. Python, how to check type of a variable. You can use the type function. So let's just do one thing. Let's just check the types. So it's working, but why wasn't it working before? Let's check it out. So it's a node type. Interesting. So it says that the value is, the hash map stores the nodes. Right. The hash map doesn't actually store values. That's interesting. Okay. That's the problem. Oh, that's why when we did string, it started working out, because it's not because the toString function of the node returns the data like that. We had to do dot data over there basically. So we had to do value dot data, and it would have worked. That's interesting. Yeah, so this time you can see that even 1 got removed from our hash map itself, and our LRU cache works. Glad to be ending this session.